ladies and gentlemen, this class recording has started. Let me move this out of the way up here and go here. There we go. All right. Yesterday, or actually Tuesday, you guys took your quiz on ionic bonding. So first, fact or features of ionic bonding. What did we learn about ionic bonding over the first couple days of this unit? So what's one thing? Positive charges attracting negative charges, okay? That's one thing we should know about ionic bonding. What else? Is that a hand or was that a, okay, good. Metals combined with nonmetals, good. What else should we know about ionic bonding? What has to happen in order for ionic bonding to occur? How do we get positive things to attract to negative things? What has to happen first? We should probably know this, by the way. What do we have to have first? The gaining or losing of electrons, right? That's what gives us those positive and negative charges to attract to each other. Last, why do things ionic bond with each other? To get to 8 valence electrons, and that's important because stable or a, why are they stable? Because they're in a, somebody want to help Tom out? Anybody? They have full stable 8 valence electrons. What does stable mean? That's how we get stable. What does it mean? It deals with what? It deals with energy. And it's a low energy state. All right? So, today we talk about covalent bonding. Covalent bonding is chemical bonding, and that means it has things in common with ionic bonding, such as it's an attractive force that holds atoms together, and it involves energy, and bonds will form if atoms have lower energy than when they're together than when they're separate, and bond formation is generally an exothermic process, right? The first Roman numeral on this outline is exactly the same as the first Roman numeral on the outline with ionic bonding because they're bonding. They have things in common. The one thing that'll be different is how it happens, and we'll get to that in just a second. Covalent bonding and ionic bonding, very similar in the intent and the end result, right? But the process is different, and we'll get to that here in a couple slides. Good here? We got this stuff? Is that a question, or you just need to finish it? Okay, go. And even though it's not up on the screen, those of you that are done, if you look at letter C on the outline, right? Bonding deals with which electrons? Valence electrons, right? Electrons in the highest energy level. And what are atoms trying to accomplish with their valence electrons? What's the magic number as far as valence electrons is concerned? 8, right? Although we said with some smaller atoms it could be 2, right? But generally 8 is our magic number, right? All right, are we good here? Like I said, nothing about these two slides is any different than the slides you saw when we were dealing with ionic bonding. So let's talk about how it's different. Okay, we're here, and let's go through. Okay. So I draw sodium up on the board, and based on our vast experience doing this so far, right, we know that sodium has how many valence electrons? Okay, and then chlorine comes along, with its 7 valence electrons, and we're all good, right? This happens like that, right? Now, once sodium loses that valence electron, it's now a what? It's a cation. It means that's positive charge. Chlorine now becomes a anion. It has a negative charge. We're all good. Okay? Somebody asked, I don't remember if it was in here or not. I think it was, but somebody asked. Okay? Oh, and we talked about, I forget who said, oh, Maya, you told us that ionic bonds happen between what kind of atoms? What kind of elements, I should say? Metals and nonmetals. Here we go. Somebody asked, why don't we see this? Okay? Answer being, in order for atoms to attract to each other, what has to be true? Why do atoms attract each other? Or what holds them together? Opposite charges, right? So in order for these two atoms to be attracted to each other, they have to have opposite charge. Here, this sodium with its 1 valence electron does not have a charge right now, right? 11 protons, 11 electrons. Same thing with this sodium atom. In order for atoms to get opposite charges, what has to happen first? Electron transfer, right? Electrons got to go from one atom to another. So, right, this would have to happen. Does that happen? No. Right? This sodium right here has 1 valence electron. What is it trying to do with it? Lose it. It doesn't even want the 1 electron that it has. It's not going to take an electron from another sodium atom. Without this transfer of electrons, there isn't one that's positive and one that's negative, and so they don't stick together. Okay? Good there. All right. Let's look at a different situation, though. Just trying to decide what color I should use. Okay? There's chlorine. We've already seen that if chlorine is there and a sodium comes around, everything's all good, right? However, no sodium around for this chlorine. It'd be good if there was some potassium around too, right? That would work out pretty well, but no potassium either. Okay? The first thing that comes around is this. Okay? All right. So we've established that chlorine with its 7 valence electrons is looking to do what? Gain how many? 1. Blue chlorine with its 7 valence electrons is looking to do what? Gain 1, right? So, is red chlorine going to transfer this electron over to blue chlorine? No. It's trying to pick up electrons, not get rid of them. Okay? Yeah, blue chlorine wants an extra electron, but it doesn't want an extra electron any more than red chlorine does. So, what's the solution? You learned the solution back in kindergarten. Right? All right. You want something, I want something. Well, no, the lesson of sharing you learned back in kindergarten. You didn't learn covalent bonding. You didn't learn covalent bonding in kindergarten. At least I hope not. Well, I mean, you could, but you learned the lesson of sharing back in kindergarten, right? Okay. So, right? Red chlorine says to blue chlorine, "Hey, you're looking to pick up an electron. I'm looking to pick up an electron." Right? This is actual like transcript of the conversation. So, I read it on the internet. You can't put anything on the internet. It's not true. Right? So. Okay. So you know what? Here. Let's work this, okay? What's mine is yours, and what's yours is mine, right? So we put this purple circle around these two electrons because, right, you get my color code, yeah? Right, yeah, okay. So, if we are sharing electrons, like I said, what's mine is yours and what's yours is mine. So red, 1, 2, 3, 4, 5, 6, 7, plus that electron that technically belongs to blue, but we're sharing, right? And so that gives red how many valence electrons? 8. Is it happy? All good, right? Blue, 1, 2, 3, 4, 5, 6, 7, plus the one that's sharing with red. Is it happy? Yep, it is, right? Go ahead, Julia. Nah, they're not sharing one. Nope, they're sharing 2.
But then, if they're both sharing at the same time, how does it work the same as atoms forming electrons that aren't being shared?
Okay, good with that? Right? That's just, a Bohr model, basically, of the Lewis structure, okay? Nope, hold on. Whoa. There we go. Okay, good there? All right, here's how it works, right? If those lines represent the highest energy levels in each of the individual chlorines, we need to have how many dots on that line? 8, because that's 8 valence electrons, right? So chlorine has its 7 reds, but if its highest electron level and this chlorine's highest electron level overlap, now that blue is on red's highest electron level. Does that make sense? Same thing with blue, right? It's got its 7 blue dots, but if its highest electron energy level blends over with red's, now it also has 8 dots on its highest energy level. It just so happens that one of them happens to be red, right? But that doesn't really matter because they're sharing these two. And so they count for both of them. All right? Good there? Okay. Now, if we go back to the very first thing that you write down or you wrote down in your outline, right? What is a chemical bond? An attractive force that holds atoms together, right? We're sharing, but is that necessarily enough to hold us together? Well, when you think about what else is going on, yeah. This Lewis structure, or this Lewis structure, right, only represents the valence electrons that are in that atom. But there's other parts of the atom, right? Specifically, what part right in the middle of it? The nucleus. What charge does a nucleus have? Right, so it's got a positive charge in here. This blue chlorine over here, right? It has 7 valence electrons, but it also has what right in the middle of it? It has a nucleus as well. Okay? Positively charged nuclei are attracted to what? Negatively charged. Well, what's the negative charge up here on the board? What are these? Those are electrons, right? Okay. This red nucleus is attracted to all of the red electrons. But guess what else it's attracted to? This blue electron. And this blue nucleus is attracted to all the blue nuclei, but guess what else it's attracted to? That red one, right? So now we have part of the blue atom part of the red atom attracted to part of the blue atom, and we have part of the blue atom attracted to part of the red atom. Yes? Is this a chemical bond? Is there an attractive force holding atoms together? Yes. Did we have to transfer electrons to make it happen, though? No. We did what with those electrons? We shared them. Okay? All right. Ready for some filling in of the outline? Okay? All right. So let's go here. All right. Ionic bonding involves transferring electrons between atoms. But as we just saw, covalent bonding involves what? Sharing electrons between atoms. Covalent bonding. Atoms will share valence electrons so that both will achieve a stable electron configuration. And as we've discussed on several occasions, a stable electron configuration can be described in a couple of different ways. Right? What are some ways that we can describe a stable electron configuration? Sorry, finish writing, then we'll talk. Ways we can describe a stable electron configuration. What could we say that would describe a stable electron configuration? 8 valence electrons. That's one way. What else could we describe it as? Lowest energy state. Or an electron configuration similar to noble gases. These would all be good for a stable electron configuration. All right? As we saw in the picture that I drew up on the board, the attraction between the shared electrons and the nuclei of the individual atoms holds the atoms together. Remember, our definition of a bond is an attractive force that holds atoms together. There's got to be some way that they are stuck together. As we saw when I put sodium and sodium up on the board originally, right? There's no way that they attract each other because there's no imbalance of electrons. There's no positives attracted to negatives, etc., etc. Okay? Good there. All right. A couple of different ways that we can represent these covalent bonds. Oh, sorry. Before we do that, one pair of shared electrons is called a single covalent bond. Right, Julia, like we talked about before. They're not sharing one electron, they're sharing 2 electrons. Okay? Come on, go ahead. Hold on a second on that. So, short answer to your question, yes, we're going to get there. All right. Good there? Okay. Here are different ways that we can represent a covalent bond. First, we just did up on the board with our chlorines. These are hydrogens, but same thing, right? Electron dot diagrams where we're showing the 2 electrons in between the 2 nuclei or the 2 atoms that we're sharing, right? Over here on the right, we have something that we refer to as a structural formula. Okay? We replace the 2 dots representing the 2 electrons that they are sharing with a straight line. That line represents the pair of electrons. So each line represents 2 electrons. Okay, go ahead. But each hydrogen has how many? 1. You have to have 2 atoms to make that bond. Each atom brings 1 electron. They always share in pairs. 1 electron from this atom, 1 electron from that atom. Does that make sense? Okay? Is that a yes or? Okay, because going back here, okay, it's not so much the sharing of the electrons that actually holds them together. It's the fact that if they're sharing these 2 electrons, part of the red atom is attracted to part of the blue atom. And part of this blue atom is attracted to part of the red atom. That's what holds them together, right? Let's say, we got a family that has, a brother and a sister, okay? And they get a combined present for Christmas, right? They get an Xbox One, right? If they both want to play the Xbox One, they share it. And it requires that they're together. We've increased family time now, right? Does that make sense? But they both have to want to play the Xbox One or else it doesn't work. Does that make sense? So, Maya, going back to the beginning of class, one of the things you said about ionic bonds is that they exist between what kind of elements? Metals and nonmetals. But covalent bonds have to exist between what kind of atoms? Nonmetals and nonmetals. Because what are both of the nonmetals trying to do? Gain electrons. That's how they share, right? If you're going to share something with somebody else, you both have to want it, right? Okay? If the parents get the brother and sister an Xbox One for Christmas, but the sister really likes playing video games, but the brother doesn't, guess what? They're not sharing it, right? Sharing requires that we both want to play the game. My good. Hold on to that question. If we got 3 different elements, we'll get to that later next week. Okay? That's when we start getting into compounds that have both ionic and covalent bonding in them. Okay? Julia, go ahead.
I don't understand why hydrogen would mix with hydrogen.
Okay, so hydrogen has how many valence electrons? 1. It's looking to do what? Nope. Even though it's in that alkali metal, right? Things are stable, small elements are stable if they have how many electrons? 2, right? So even though it's listed way over on that alkali metal side, if it loses that electron, it's really not stable because then it has how many? 0, and that's not good. Okay? So even though it's listed over there, right? Hydrogen and hydrogen are both looking to pick up 1. So in a lot of ways, hydrogen is a little bit more like what kind of family on the periodic table? More like, well, which family of nonmetals specifically? Halogens, right? Because what are halogens looking to do? Things in group 17 are looking to pick up how many electrons? 1, right? So in different situations, hydrogen can act like a halogen, but in some situations, it can act like an alkali metal. So it could almost be listed in either place. We usually see it over on the left-hand side, though. Once you get past carbon, okay? Because once you get past carbon, everything should have enough, because remember the smaller ones only want 2 because we're dealing with the 1s orbital, and 1s orbital can only hold 2 electrons. But once you get past carbon, now we're into the 2p's, and that now we're going to get up to 8. Okay, does that make sense? Yeah. My good. Oh sure. Yep. So we could go here. Actually, that's a good transition, all right? So here's hydrogen, okay, and here's chlorine. All right. Chlorine's looking to pick up 1. Hydrogen's looking to pick up 1. Okay. There we go. Usually, no, that doesn't work really. Okay, just doesn't. Okay, theoretically you could, but we usually don't see it. Okay. Okay, good. Okay. Well, let's do this first, and then we'll get to that. Okay. All right. So. All right. Let's get out of here. Let's go here. Come on. Okay. We call this group of atoms held together by covalent bonds a molecule. Group of atoms held together by 1 or more covalent bonds is a molecule. And Maya, if these atoms are being held together by covalent bonds, that means what kind of elements are they going to be? Nonmetals. Molecules consist of nonmetals because they are being held together by covalent bonds. So here's some pictures of some molecules. Some that you probably know, like this one right down here in the bottom right-hand corner. Yeah? H2O, right? Because there's 2 hydrogens and 1 oxygen. Okay? All right? This is ammonia. Like if you ever use ammonia, like that's this compound dissolved in water. It smells really bad. Okay? Yeah. Okay. And then this is actually hydrogen chloride, and we'll talk about that later on. It produces cyanide, and you don't want to do that.
Yeah,
so.
I just want, like, I knew it produced something illegal. I was just
Yeah.
wondering, like, what?
Cyanide, you don't want to do that. So
Cyanide and
you don't want to do that. Trust me. So yeah, if you go home and you see like in the cabinet underneath your sink or something like that, hydrogen or ammonia and bleach next to each other, be like, Mom, get out. So, Mom, we can't do this, all right? Like, put the bleach by the clothes, put the ammonia somewhere else.
what if you mix the 2 together in, like, a controlled area? Don't stop at crystallized.
No, don't do that. No. All right. So next, a specific type of molecule we refer to as a diatomic molecule. And as its name suggests, and as the definition up on the board states, it is a molecule that consists of 2 of the same kind of atoms. We have already seen 2 kinds of diatomic molecules up on the board already today. The first example I drew up for you on the board was a bond between which 2 atoms? Chlorine and chlorine. It's a molecule because it's because it's a covalent bond. It's a diatomic molecule because it's 2 atoms that are the same. Question: if chlorine forms a diatomic molecule, well, it will bond to itself. Can you make an educated guess about other types of elements that might form diatomic molecules? What else? What other elements might form diatomic molecules? We know chlorine does. What else? Well, let's go specifically, right? So what are we looking at now? Halogens, right? Fluorine. What else? Bromine. What else? Iodine, all right? So those 4 definitely form diatomic molecules, okay? We also saw what else that we drew up on the board? Hydrogen as well, so that's 5, okay? Good with that so far. Okay, let's take a little break from the outline and go back to some pictures, okay? By the way, I should have probably had you guys draw these pictures. The back of this outline is completely blank, so you can use that. But I'm going to draw a couple other pictures up here on the board that you might want to draw just to explain some things. Okay? All right. So, okay. Here's oxygen. And based on oxygen's location on the periodic table, you should be able to tell me that it has how many valence electrons? 6. I probably should have asked you that question before I drew it up on the board, but whatever. All right? So, it'd be great if a calcium came along, right? Because based on calcium's location on the periodic table, how many valence electrons does it have? 2. Okay? And everybody'd be great then, right? But there are no calciums around. I know. It's disappointing. The only thing that's around is another oxygen. So, both of these oxygens are looking to do what? Gain how many? 2. So red oxygen says to blue oxygen, hey, so I heard this story, again, this is the actual transcript of the conversation, okay? So I heard this story about these 2 chlorines that were both looking to gain an electron, and they shared. So, well, what do you think? So, blue, yeah, it's like red is hitting on blue, kind of, like, you know, like, yeah, so, you know, so I heard about these chlorines, all right? So, okay, we do this, and so now we said, right, what's mine is yours and what's yours is mine, okay? So oxygen, 1, 2, 3, 4, 5, 6 valence electrons of its own, and got that 7th one there. And oxygen, 1, 2, 3, 4, 5, 6 of its own, and that 7th one there. So blue says to red, hey, yeah, this is great. I'm glad you suggested this, but I'm not really happy with this arrangement, right? So red goes, well, so it worked pretty good the first time. What do you think? Right? Blue's like, well, if one's good, right? 2 is better, right? Okay. So now we are not sharing a pair of electrons, right? We're sharing 2 pairs of electrons. Okay? And we have given this the very descriptive name of the double covalent bond. Okay? Yeah. All right. So, let me tell you another story. Easy, everybody. Still got like 4 minutes left. Easy. So, nitrogen. Nitrogen comes along. No, not totally different situation. Not those 2 oxygens anymore. So you find nitrogen on the periodic table, and you find out that nitrogen has how many valence electrons? 5. And if aluminum was around, right, everything would be great. But there is no aluminum around. Hey, let me finish. The only thing around is another nitrogen. So, red nitrogen goes to blue nitrogen. Hey, I heard about these 2 chlorine atoms that shared a pair of electrons to get a stable electron configuration. And red goes, yeah, I heard, or sorry, blue goes, yeah, I heard that story. I also heard that these 2 oxygen atoms shared 2 pairs of electrons to get stable electron configuration. So blue then goes to red. You thinking what I'm thinking, or right? Okay. So, any guesses about a cool name that we could call this? A triple covalent bond. Whoa. I know. I know it's hard to figure out sometimes how we come up with these names, like, you know. So real quick, let's finish this up. I know it's almost the end of the period, but we can do it. So, first, there are 7 elements on the periodic table that form diatomic molecules. Right? Fluorine, chlorine, bromine, iodine, your 4 halogens. Hydrogen that we talked about already, but then also nitrogen and oxygen. There are 7 elements on the periodic table that form diatomic molecules. Even though there are other elements in the families of nitrogen and oxygen, we don't see them form diatomic molecules. And then, in the process of forming those diatomic molecules, we also talked about multiple bonds, where atoms are held together by sharing more than one pair of electrons. Double bonds are where atoms share 2 pairs of electrons, or 4 electrons total. Triple bonds, atoms share 3 pairs of electrons, 6 total. Okay? Real quick, as the bell's about to ring, there is a homework assignment on the calendar for tonight. It's some reading from the book and a couple of just general questions about covalent bonding. We'll talk about names and formulas tomorrow.